In the first two videos, we saw the Weierstrass representation and the DPW method. These two algorithms take as input data holomorphic functions, and the resulting surface is a conformal, minimal or CMC immersion into one of the spaces R3, H3 or S3. In this video, I would like to describe the construction of three examples. Each one has its own features, each one lives in one of the three ambient spaces, but each one is done using a desingularization procedure involving a mix of a Weierstrass type representation and the implicit function theorem. First, let's go to R3 with minimal surfaces and recall the Costa surface that I've showed you in the first video. We saw that the Costa surface is an embedded genus 1 surface, but that it's actually one member of a huge family of minimal surfaces in R3. From the Costa surface, you can increase the genus by adding some necks, but you can also increase or decrease the number of catenoidal or planar ends. And each example has a weight corresponding to the neck size of these little catenoids. If you decrease the weight, then the surface converges to a multifold cover of one plane with double points at the places where catenoids were. On this picture, making the weight converge to 0 will make a triple cover of a plane with 3 double points between the first and second plane and 1 double point between the second and third plane. All these examples were discovered in the 1980s and they are all symmetric. They all have a rotational symmetry. And the question at that time was the following. Is the Costa family even bigger, and does this Costa family contains non-symmetric minimal surfaces? The answer to that question is yes. In 2002, using the Weierstrass representation, Treze showed that there exist minimal surfaces in R3 which are complete, properly embedded, have finite total curvature, and no symmetries. All these surfaces are obtained with a desingularization procedure starting at the singular surface consisting of some planes with some double points. And the simplest example of a non-symmetric surface is given in the paper of Treze. It is constructing from 5 planes with 4 catenoidal necks between the first and second one, 36 between the second and third one, 8 between the third and fourth one, and 1 between the fourth and last one. Because these surfaces were constructed 20 years after the discovery of the Costa surface, you can imagine that the Weierstrass data is not explicit at all. But still, these surfaces are constructed with the Weierstrass representation. So let's take a look at the proof. The idea of the proof is that the Weierstrass data for a catenoid is explicit and the Weierstrass data for a plane is also very explicit. Starting with a combination of these Weierstrass data, which are very simple and very explicit, one can perturb these Weierstrass data and get a new minimal surface close to the singular configuration. So first of all, we have to guess the form of the Weierstrass data giving this non-singular surface. In particular, we have to guess what will the underlying Riemann surface look like and what the Weierstrass data on this Riemann surface will look like. In the case of this kind of surfaces, the underlying Riemann surface at t equals 0, which means at weight value equals 0, which means at the singular configuration, the underlying Riemann surface at t equals 0 is a Riemann surface with nodes. You take a copy of the Riemann sphere, another copy of the Riemann sphere, and a third copy of the Riemann sphere. You put 3 points on the first, 4 points on the second, and 1 point on the last one. And you put one Riemann sphere between couples of points corresponding to each catenoidal neck. And there exists a technique called opening nodes, which allow you from this singular configuration to open the node for a value of t greater than 0, which will make a Riemann surface having the same topology as this minimal immersion. Of course, there are a bunch of parameters that you don't know. For example, you don't know exactly where you will put on your Riemann surface this little nex here. And because you don't know this parameter, you can put the value of this parameter into a vector x containing all your unknown parameters. You can do the same with the holomorphic potential of the Weierstrass representation. At t equals 0, meaning at the singular configuration, you know exactly what is the potential of a plane, and you know exactly what is the potential of a catenoid. You have thus the form of your Weierstrass potential at the order 0. You can then perturb it at first order, adding t times some other potential, and of course there are a bunch of parameters that you don't know that you can put in your big vector x of n known parameters. Now, at the end of step 1, you have a Riemann surface M, which depends on a real parameter t close to 0, and which depends on a bunch of other parameters assembled into the vector x. You have also a Weierstrass potential depending on t and x. So you could run the Weierstrass representation with these data, and you will get a family of minimal immersions into R3 depending on t and x. But of course, the Riemann surface M is not simply connected. So the immersions that you will get will not close. They will be well defined only on the universal cover of M and not on M itself. All that to say that you have a period problem to solve. And step 2 of this construction is to encode this period problem into several equations depending on t and x that you can put in a big vector E depending of t and x. From here, the idea of Trezé is to use the implicit function theorem at t equals 0 in order to solve the period problem E of tx equals 0. To do that, we first need an initial value for x solving the period problem for t equals 0, which is step 3. And remember that t equals 0 corresponds to the singular configuration. And the singular configuration is made out of planes and catenoidal necks. Because the Weierstrass data of planes and catenoids are explicit, it is not so hard to find an initial value for x0 satisfying the closing condition. Now the fourth step of the construction is to compute the derivative of E at t equals 0 with respect to the vector of parameters x at x0. If this derivative is surjective, then you can use the implicit function theorem and get a vector x, now depending on t, such that x of 0 is x0, and such that E of t and x of t equals 0. Now you have a one-parameter family of Riemann surfaces depending on t, and a one-parameter family of holomorphic Weierstrass potential depending on t. And because you use the implicit function theorem to solve E equals 0, you know that the resulting immersion f will be well defined not only on the universal cover of M, but on M itself. At t equals 0, this immersion is singular and will give you the triple cover of a plane, with some double points. But if you started from a non-symmetric configuration at t equals 0, then you know for sure that for some small values of t, the immersion f constructed is a non-symmetric minimal surface in R3, which proves the theorem. This was the first example that I want to describe, which uses a desingularization procedure. Let's look at a second example, and for that, I need to show you the picture of a tetranoid again. This is a tetranoid constructed by Nick Schmidt, using the DPW method in the Euclidean 3 space with constant mean curvature 1. It has 4 Delaunay ends with small necks. And you can see this surface as a central sphere with 4 Delaunay ends attached to it. Each one of these ends has a direction, and each one of these ends has a weight. As for the Costa surface, this one is very symmetric, and one could ask the question, does there exist n-nodes without any symmetry? We'll see that here again, the answer is yes. Take a natural number n greater than 2, and take a vector τ composed of n real numbers. Take an n-tuple of unit vectors v in R3, and assume that τ on v satisfy the following balancing condition. Then there exists a smooth one-parameter family of complete CMC h equals 1 immersions in R3 with n Delaunay ends delta such that the weight and the direction of each end satisfy these two equations. The limit value of the weight I is 0 and the derivative of it is τi, and the limit value of the direction of the end is vi. If this theorem is true, then that means that you can start from the unit sphere in R3, choose a bunch of directions on this sphere, a weight for each direction, and if your configuration is not symmetric, then you have made a non-symmetric n-noid. Let's look at the proof of that. It is exactly the same as before. First, you have to guess the form of the data. In particular, what will be your Riemann surface and what will be your holomorphic potential. Here, we are making non-minimal surfaces in R3, so we will use the DPW method. The underlying Riemann surface is the Riemann sphere minus n points, but again, because you don't know the position of these points, you have to put them into a vector of n-known parameters x. The DPW potential at t equals 0 should be the potential giving rise to a sphere. Perturbing this initial potential at first order of t and using a set of n-known parameters x gives you a 2-parameter family of DPW potentials. You have now a family of Riemann surfaces depending on t and x, and a family of DPW potentials depending on t and x. So for each value of t and x, you know that you will get a CMC immersion in R3. But again, the problem is that the Riemann surface M is a punctured sphere. It is thus non-simply connected, and the family of immersions you will get will not be defined on M, but on its universal cover. To solve that problem, you encode the monodromy problem equations into one big vector E, and you want to solve E of t and x equals 0. Again, from this point, the idea is to apply the implicit function theorem, so you have to satisfy its hypothesis. First of all, you have to find an initial value for your vector of parameters x, such that E at t equals 0 and x equals x0 is equal to 0. And you can do that because everything is pretty explicit at t equals 0, even if everything depends on x. For the same reason, you can compute the derivative of E at t equals 0 with respect to x at the initial point x0, and if this linear map is surjective, then you can use the implicit function theorem. Now your vector x is a map depending on t, such that at t equals 0, x is x0, and such that E of t and x of t is 0. You thus have a one-parameter family of CMC immersions into R3, which are well defined on the n-punctured sphere M. At this point you have an n-noid. You have a CMC surface which is defined on the n-punctured sphere and has n ends. But you don't know anything about the geometry of this surface. So with analytical tools, you can study this vector x of parameters and following it into the 3 steps of the DPW method in order to say something about the immersion f that you get. And if you do that closely, then you can show that the ends of the surface you just have constructed are embedded under certain conditions, which allows you to prove that there exist complete embedded CMC enoids in the Euclidean 3 space without any symmetry. And what is the big advantage of the DPW method? It's that it is roughly the same regardless of your ambient space. So the same procedure can be carried out in H3 in order to make complete embedded constant mean curvature enoids without any symmetries. And this is the second example I wanted to show you. Let's make our last example of this video, this time in the 3-sphere. In 1970, using the solution of the Plateau problem, Lawson showed that for each pair of natural numbers m and k, there exists a compact orientable minimal surface xi mk of genus m times k embedded in S3. On this picture, I have put the first Lawson surfaces for small values of m and k. Each of these surfaces is shown in R3 after having stereographically projected the minimal surface from S3 to R3. The first one is the Clifford torus and is exactly xi 1, 1. The second one, in blue, is xi 1, 2. And it is the same after an isometry of S3 than xi 2, 1, which is on the bottom left here. The next one, in red, is xi 1, 3, again, which is the same as xi 3, 1. The last one, in yellow, is xi 2, 2. Now these surfaces were made using the Plateau problem. But because the DPW method allows for the construction of all minimal surfaces in S3, there should be a DPW potential leading to these Lawson surfaces. The only problem is that these DPW potentials are highly non-explicit. So you cannot use a Lawson potential as the starting point of a desingularization construction that we saw earlier. Nevertheless, you can still do something by looking at xi 1g for big values of g. Let me show you, for example, a picture of xi 1,8. As you can see, this looks a lot like xi 1,2 or xi 1,3 that I showed you. And you have in the center of the surface the genus which is accumulating. So in order to see the genus as you increase the value of g, you have to zoom in on the surface. And doing that, you should recognize a surface that we saw on the first video. This surface looks a lot like the Shirk surface, a minimal surface in R3. And the nice point about the Shirk surface is that we know its Weierstrass data explicitly. And because the DPW method is a Weierstrass type representation, you can make the link between the Weierstrass representation and the DPW method in order to construct high genus Lawson surfaces. To make a high genus Lawson surface, your parameter t is the inverse of the genus. So starting at t equals 0 is the singular surface that after a blowup is a Shirk surface. Again, I have put here the steps of the proof, but these are exactly the same as the last two examples we constructed. And one advantage of constructing the Lawson surfaces like that is that once you have found the values of your parameter x after applying the implicit function theorem, you can do an analysis on them and follow the steps of the DPW method in order to have an idea of the area of the surface you just constructed. And using this method, Lynn Heller, Sebastian Heller, and Marta Treze found an algorithm to have the Taylor expansion of the area of the Lawson surfaces xi g1, as g tends to infinity. This completes the picture I wanted to show you, so I would like to thank the organizers of this conference, and I would like to thank you for watching.